All right, we're going to start on page 15, number 6. It's giving you an acceleration time graph, and it's giving you a velocity time graph, and it's asking if there is anything wrong with this, and if there is, let's just identify it, right? Well, if you look at, I'm going to break this down into sections. So I'm going to break this into A, B, C, D, E, F, G, I guess, right? So now, for part B and D and H, I guess, there is no acceleration. For part A, the slope of this segment here should give us the acceleration. So the acceleration here is positive. The acceleration here is 0. This acceleration should be negative. For D, it should be 0. E, it should be negative, 0, positive. It's just the slope, basically, right? So what's wrong with this picture here is for E, yeah, this part here is good. That's a positive slope. This part here is good. That's a negative slope. This part here is no good. This should be a negative slope, okay? And for the last part, it should be a positive slope. That's what's wrong with it. Okay. Now, this is a velocity time graph for number 7. It's talking about velocity time graph and acceleration time graph. Okay, so we're going to try to sketch the acceleration time graph. So for the first time interval here, so we have a positive acceleration, so I'm just going to mark it here. Okay. And then it's going at a constant velocity for the next time interval, so drop here, go across the x-axis or the time axis, right? And for the next two intervals, you have a negative slope, but it's not as steep as in the very first part. So it should drop, but it's not going to be as high as for the first part. So it should be something like this. Right? Hello again. Okay, today we're going to talk about interpretation of graphs, motion graphs. In other words, position time, velocity time, and acceleration time. And we're going to see how we can go from one to the other, right? Now, before we start this, I want to talk a little bit again about this PVA that I talked about in the past. So P stands for position, V stands for velocity, and A stands for acceleration. And then let me just write it out down first, and then I'll talk a little bit about it. So what does this mean? This is just a quick shortcut for you guys to know how to analyze these graphs and how to get information out of the graphs. If you have a position time graph, and if you take the slope in that position time graph, that will tell you some information about your velocity. If you have a velocity time graph, if you take the slope, you get the acceleration. Going the other way is a little tricky, because when you do an acceleration time graph, you don't actually get velocity, but you get the change. So I'm going to put a delta here. So when you do acceleration time graph again, you get a change in velocity. And when you do a velocity time graph, you do a change in position. And a change in position is just displacement. And we talked about all this in the past. So I'm going to be relying on this a lot to analyze some of these graphs. Not here, but later. So here it tells you to replace d with x. In other words, this is not distance, it's position. But in this case, we can say that the distance and the position are the same thing because we're just traveling in the positive direction. So in this here, it says the first line has to describe velocity, second line has to describe acceleration, and the third line has to say what kind of motion. Is it uniform motion, meaning if you're going at a constant velocity, that's uniform motion. If your velocity is changing, we call that variable motion. And if there is no motion, then there is no motion. All right, so let's look at the first line. I'm going to go back to this. Actually, I can probably use this. If you have a position time graph, the slope gives you the velocity. Well, you look at the slope here, it's a constant slope. In other words, it's not a change in slope. So I can say that the velocity is constant, and if the velocity is constant, there is no acceleration, and the motion will be uniform. I'm just going to abbreviate. If I'm looking down here, it looks like as the time passes, this curve is getting steeper and steeper in time, which means my velocity is increasing. And if the velocity is increasing, I'm accelerating. And if I'm accelerating, I'm dealing with a variable motion. So I want you to pause the video for about 2 minutes. Try this problems here, but I'm going to keep going. So pause the video for 2 minutes and try this. It shouldn't take you 2 minutes, but if you need 2 minutes, it takes you 2 minutes. Here, there is no motion here. In other words, you're stuck in this position. The time passes and you're stuck here. Okay? So there's no motion, no acceleration, and there's no motion, period. Here it looks like the steepness is getting less as you travel in time. So steep, less steep, less steep, less steep, less steep. So you're reaching a plateau, basically. So this looks like as the velocity is decreasing, you are decelerating because you're slowing down, and it's a variable motion. Now this is where you have to be super careful. Now we're changing from a position time to a velocity time. You cannot look at these graphs the same way. They are very different. Okay? This is a velocity time graph. You can see clearly that as the time passes, your velocity increases. I hope everyone sees that. So think about it. As the time passes, your velocity increases, and which means you are accelerating, and it's variable motion. In here, I can see the time passing, but my velocity is stuck at the same number, so constant velocity. And if you notice down here, it was no motion. But if it's a VT graph, that's a constant velocity. And there is no acceleration because you're not changing your velocity, and this is a uniform motion. This one, you can see that the velocity is dropping. I think you got the idea. You are decelerating, meaning you're slowing down. Not uniform, but variable motion. And here, you're right on the time axis, which means your velocity is 0. So basically, nothing is happening. The object is not moving. Now, we're going to look at the bottom part of this graph, of this page, and we're going to answer the questions. So it says, for each of the axes below, draw the graph corresponding to the description on the left. We might have more than one answer for these problems. It says decelerated. So all I have to do is that I have to show something that has less and less of a slope in time. As the time passes, the slope in the position time gets less. So I can do maybe something like that, right? But it will not be a straight line though. Or it could be something like here in red. Okay? Here it's uniform motion, which means the slope is constant, and the only way you can get that is by doing a line. And it doesn't have to start at 0, by the way. Or this. Or it could be any line, it could be under the time axis, right? Okay. Increasing speed, so I have to show something that has an increasing slope in time. So it has to be a curve like this, or the other option is maybe something like that. Anything that gets steeper in time is good. Variable motion, you pretty much have the first one and the third one. So I'm not going to draw that, you got the idea. Any one of those is valid. Okay, let's look at this guy. All right, for number 8, it's giving us a graph, but it's not labeling it. Okay, so it's saying if the vertical axis is position, does the object ever change direction? So if I put position here, I guess I call it X. It looks like the position is starting from high numbers and it's going down to low numbers, right? And then it changes. It starts to go from low to high. So yeah, we are changing direction in this case. So we're going from high to low, then we're going from low to high. And the only way you can do that is by changing direction. Another way you can look at it is the velocity at this point here is 0. The velocities here are negative. The velocities on this side are positive. So you cannot go from the negative numbers to positive numbers without passing through 0. If the vertical axis is is velocity, does the object ever change direction? So if this is a velocity time graph, you do change direction each time you cross the time axis. So yeah, you do change direction at 2 seconds and at 8 seconds. Okay. So just be careful how you read these graphs. Number 9. Okay. These are velocity time graphs. Okay, so we're going to rank this based on the displacement. Now, if you have a velocity time graph, the displacement is just the area between the curve, the line basically, and the time axis, right? So I'm going to look at each box as one square unit. So I have 1, 2, 3, 4, 5, so that's a 5, okay? But it's a negative 5, okay, because it's below the time axis. This is going to be, I'm just going to find this area here. So it's, what is that? 1, 2, 3, 4, 5. So what's 1/2? 5 times 1 1/2. Okay? So, and that's going to be a positive number. So what is it going to be? 2.5 times 1.5. Okay, so 375. So this is 375. This one here looks exactly like the one we just talked about now, except that it's negative. Okay. This one here is okay. So it's 1, 2, 3, 4, 5 times. It looks like it's 1 1/2. So that's 7 1/2, and it's positive 7 1/2. This one here, you're going to end up with some negative number here and an equal number but positive on the other side. So this one should give us 0. This one is the area of this triangle here. So it's 1/2. 1, 2, 3, 4, 5 times the height, which is 1. So that should be 2 1/2. Okay. So if we're going to rank them, it's going to be, should be D first, then comes B, then comes F, then comes E, and then C, and then A. Okay. Now you just got to be careful here. If it did say the magnitude of displacement, you turn all these negatives into positives, and then you rank them. So just be careful whether it says magnitude or just says displacement. Velocity time graph. Now this is talking about the distance traveled. So which means we don't care about the negatives. We don't care about which way we're traveling. So if I'm walking 5 steps either right or left, it's still 5 steps. But in terms of displacement, that could be a positive 5 or a negative 5. All right. So basically here to find the distance, I'm just going to find the displacement for these things here. And turn it into a positive number and add. So this one is going to be positive 5, basically. Okay, well, it's negative 5, but after you change it, it becomes positive 5. This one is going to be 1/2 base, which is 5 times height, which is 1.5. So that's 375 positive. This one is going to give me 375 negative, but in terms of distance, it's positive. This one, I think we did earlier. This is 7.5 positive. This one, you're going to find this area and add this other area to it. And you're going to make both of them positive. So this is going to be half the base, which is 2.5 times the height, which is 1. but I have to add the other piece to it, so it's going to be twice as much. So this is just going to be positive 2.5. That's the distance. This one is going to be half base of 5 times the height of 1, so this is going to be 2.5. So in terms of distance, it looks like D goes first, then comes A, B and C are equal, and then and E and F are equal and less. Okay. Number 11, I think this one is done in the previous video, but I'll go over it again. So if you throw something up in the air, when it reaches the highest point, it has to change direction and come back down. This velocity time graph is not showing you that it's changing direction. So basically what this is showing you is you throw it up in the air, it slows down, it gets to the highest point, its velocity becomes 0, and it just decides to keep going up at a higher speed. Okay? So a correct way of doing this graph would be that. Okay? So you throw it with a certain speed, let's say up is positive, it starts to slow down. When it gets to the top, its velocity becomes 0, and it changes direction, and it comes down the other way. So down is negative, so that's why your velocities are negative. All right, number 12. All right, here again, it doesn't tell us what kind of graph it is, but they keep changing it. So if the vertical axis is position, okay, so if I make this position here, okay, does either child ever change direction? No, they don't. And the reason for that is because position is increasing in both cases. It never kind of like increases and then it decreases. It just keeps going up. Another way you can look at this is that the slope of either one of these lines always remains positive. It never turns into 0 and becomes negative. If the vertical axis is position, are the two children ever at the same position? Yeah, sure, they're going to be at the same position here, which is about 2 seconds, and here, which is about 9 seconds. Okay. If the vertical axis is position, do the two children ever have the same acceleration? The answer to that is no, because Ariel has no acceleration, going at a constant velocity. Byron is constantly changing speed, so there will be an acceleration for Byron, but no acceleration for Ariel. If the vertical axis, if the vertical axis is velocity, do the two children ever change direction? So if this is velocity, they will change direction when they cross the the time axis. So Ariel will do it at 5 seconds, and Byron will do it at 6.5 seconds. If the vertical axis is if the vertical axis is velocity, do the two children ever have the same velocity? Okay. Yeah, they're going to have the same velocity when their curves intersect. So it's going to be at 2 seconds, and it's going to be at 9 seconds. Okay. If the vertical axis is velocity, do the two children ever have the same acceleration? Okay. I think I skipped C here. Yeah, I'm going to go back to C. Okay. Yeah, let me finish. Actually, I'll go back to C. If the vertical axis is position, do the two children ever have the same speed? Okay. Yeah, they will have the same speed when their curves have the same slope. So if you think about it, if you do the tangent somewhere in here to this curve, okay, that's going to have the same slope as the line for Ariel. Okay. So yeah, they will have the same. They will have the same speed around, I would say, about 6 seconds. All right, now we go back to the G. If the vertical axis is velocity, do the two children ever have the same acceleration? Yes, they do. And basically, in a velocity time graph, the acceleration is given by the slope of the curve. So if I take the slope here, if it's velocity time, that's going to give me the acceleration at this point here. And this line will be parallel to that line, so which means they're going to have the same acceleration. Hello everyone. Today we're going to talk about the graphical analysis of motion graphs. So we're going to talk about position time, velocity time, and acceleration time graphs. And we're going to see how we can go from one to the other. And I want you to understand that all three kind of graphs give you different information. So you have to really be careful about what graph you're looking at. So this is a speed time graph, and we're going to try to use this idea here. So if you have, I'm going to talk a little bit about this. If you have a position time graph and you want to find the velocity, you do the slope. If you have a velocity time graph and you want to find the acceleration, you do the slope. If you have an acceleration time graph, if you do the area between the curve and the time axis, you're not going to get the velocity, you're going to get the change in velocity. And if you have a velocity time graph, and you do the area under the curve, or between the curve and the time axis, you're going to get the change in position, which is just another way of saying displacement. So let's take a look at this. This is a speed time graph, so you got to be careful with that. Now, here it says, what's the acceleration between 4 and 6 seconds? Well, between 4 and 6 seconds, the acceleration is the same as between 4 and 7 and 4 and 8. So all I have to do is find the slope of this segment here. Okay? And the slope of that segment is a rise of 10 and a run of, this is 9, I think. Okay, and this is 4. So it's 10, okay, and a run of 5. So that should be 2 meters per second, which means your velocity is increasing by 2 meters per second every second. Okay, the next thing it says, when is the object traveling with the fastest speed? A lot of people make the mistake and they say, well, it's traveling with the fastest speed in this time interval here, right? So that's between 12 and 15. That would be true if this were a position time graph, but this is a velocity time graph. So with velocity time graph, if you want to figure out your speed, you just read the graph. And your highest values happen to be up here. So it's between 9 and 12 seconds. A lot of people fall for that. All right, so I don't want to scroll, so I'm just going to look at my notes here. At what time is the object not moving? Well, it seems to be that the object is always moving. It will not be moving if it cuts the time axis. In other words, that's where the velocity would be 0. But it's always moving. Okay. And a lot of people will say, well, it's not moving up here, down there, and down there. That would be true if this were a position time graph. Okay. When does the object have a constant positive acceleration? You want to find acceleration from a velocity time graph, do the slope. So you just have to figure out which slope is positive. So the slope is positive here, and that's it. So it's between 4 and looks like 9 seconds. Does the object have a constant negative acceleration? Same concept. You have to figure out when is the slope negative, and it's between 12 and 15 seconds. So what's the displacement of the object from 12 to 15 seconds? This is another tricky one. So from 12, I should have erased this. From 12 to 15, you have to find the area of this whole shape. What a lot of people do, they only find the area of that triangle. You have to get yourself all the way down to the time axis, right? So you probably found 22 and a half, but it should be 25 and a half because you probably missed this part here, which is 3 meters per second. 3 meters, sorry. What is the object's velocity at 8 seconds? Again, since this is a velocity time, you just read the graph. It should be 14. If this were a position time, you would have to find the slope of this segment. Because if you want to find the velocity from a position time, you do the slope. What's the meaning of the number 6? It means this number 6 here. This means like when the clock starts, the speed is 6 meters per second. So that's pretty much your initial velocity. All right. the next page. All right, let's look at number 13. The graphs represent the velocity of two toy robots moving in one dimension for a particular time interval. Both graphs have the same time and velocity scales. Is the magnitude of the displacement of the robot in case A greater than, less than, or equal than that of in case B? Okay. So if you want to find the magnitude of displacement, so we have to find the displacement here, turn it into a positive because it says magnitude. Find the displacement here, okay, and add them together. So the displacement here, it just looks like 1/2, 1, 2, 3, 4, base times the height of 3. So that should be just a 6. And this is a 6. Well, this is a -6, but in terms of magnitude, you make it a positive 6. So this is going to give us a positive 12. This one here is going to be 1/2. The base, which is about 2.5, times the height, which is 2. So this is 2.5. This part here is 1/2. The base, which is 1, 2, 3, 4, 5.5. Okay, times 4. It looks like. So it's 2 times 5.5. So that's 11. So 11 and 2.5 is greater than 12. So the magnitude of displacement is greater in case B. Or less in case A. Okay. Let's look at number 14. The graphs below show the velocity of two objects during the same time interval, right? So here to find the displacement, we technically just find the areas here. So this is 1/2 base times height, so this is a 1. What we got here? This is a trapezoid, kind of, so you can do the area of the trapezoid. So that should give you about 4 units for the area. In this other trapezoid, it's what is it, 2 plus 4, that's 6, divided by 2 times 2. So this is a 6, basically, right? So the displacement is greater for object 2. All right, number 15. The graphs below show the position versus time for 6 boats traveling along a narrow channel. Scales on both axes are the same. In each graph, 2 points are marked with dots. Okay. Rank the situation with the basics of displacement. Now, if this is a position time graph, to find the displacement, all you have to do is do the change in position. Okay? You don't do the area. You just got to be careful here. This is not a velocity time graph. This is a position time graph. So now, if you do the change, you do the final, which is 0, minus the initial position, because this comes first. Okay? In here, it should be, I don't know what I did in the answer. Okay, I think I made that 3/4. No, I'm sorry, 1.5. Okay, so this is going to be negative 1.5 minus negative 1/4, or 0.25, basically. Yeah, I think that's what I did. In here, this position here is, it looks like it's 1.5 minus half, basically. Okay? In this position here, it looks like that's, I don't know what I did here. I think I made that 1/4, basically. So negative 1/4 minus negative half. Okay. In here, this is negative 1 minus 1. Okay. This is 1 here. Okay. This here, it looks like it's positive 1.5 minus the initial. It looks like it's what do you call it? 1.75. It looks like. Okay. Yeah, that's what I did. Okay. So you just have to calculate this and rank them, and you have to keep the negatives in there. So the ranking should be B, A, E, and then F, D, C. Okay. So just the only thing you have to be careful here is what kind of graph you're dealing with. This is a position time. To find the displacement, you just do the change in position. Okay? If it says magnitude of displacement, you do the change in position and you drop the negative signs. So now this is a position time. Okay? It has to be looked at differently than a velocity time. Now here it says describe the motion in each of the three segments. Of the segments, three ways. You have to figure out what the direction is, whether you're speeding up, slowing down, or you're going at a constant velocity, and is your acceleration positive or negative. From A to B, you're not going anywhere, right? And that's the same thing from F to G. So let me just show that here. So from A to B, okay. From A to B, and from F to G, same motion, right? Are you speeding up, slowing down, or constant velocity? Well, you're not going anywhere. And there is no acceleration. Same thing down here. Okay. From B to C, it says that this is a line, which means your velocity is constant, right? Because in a position time graph, your velocity comes from the slope. So from B to C, you're going at a constant velocity, and you're doing that in the positive direction. You can look at that two ways. Your position is increasing in time, or you can see that the slope is positive. It's a unique slope here. So which means, and the slope is velocity, so you're moving in the positive direction. And you have no acceleration because you're going at a constant velocity. If you look at E to F, is the same idea. So, except that here you're moving in the negative direction, because your position drops, or you can see that your slope is negative. So this is negative, but you're doing it at a constant velocity with no acceleration. From C to D, you can see that you're still going in the positive direction, your position is increasing, or you can see that your slope, even though it gets less, it's always positive. So you're going in the positive direction, but it looks like you're slowing down, because here's the steepness here, and it gets less and less and less steep. So you're losing speed. Now, think of this as a positive. This is a positive thing. Think of this as a bad thing. So the product of these two is a bad thing. So that's a negative acceleration. And from D to E, you're going in the negative direction. Position is dropping, or the velocity is negative, and the other thing is, your velocity is increasing because your steepness is getting more and more in time. Okay, bad, good, bad. Okay, next video. Next graph. Okay, describe the motion in the 4 parts of the graph below. The scale for time is 1 second for each box, and scale for distance is 10 meters for each box. So 10 meters for each box here, and 1 for each box here, 1 second for each box. What's the meaning of the D-intercept? Well, this just means that when the clock started, you were at the origin. Now I'm going to try to sketch a velocity time. Now I can see that the slope here is negative. So which means I have to allow some room below the time axis. So velocity, meters per second, the time in seconds. Okay. Here, my velocity is changing. It's increasing in time. So my graph should look something like this. Okay. In here, my velocity is constant, so my graph should be pretty flat. Okay. But the steepness of this line is much less than the steepness here. So there should be a drop here, and then a straight line. And you can put the times in there. The value, this value here, you should be able to calculate that by doing the slope here. So 1, 2, 3, and so it's 30, 2, 4, 6, oh, can't count. 2, 4, 6, 8, 9 it looks like. So it's 30 over 9, you can figure that out. Okay? And here, you're not going anywhere, so it looks like this. And you will have to put the times here. And here it's a negative slope of 2, 3, 4, 50 over 4. So you will have to come here and do negative 50 over 4, which is 12 and a half, down, and just draw a line. That's how you do it. Okay. All right, next page. Chris, make sure we stay recording. Okay. Now we're going to analyze this other graph. It says find the displacement and acceleration at 2, 6, at those times basically, 2, 6, 12, and 14 seconds. Now this is a velocity time. I'm just going to show the graph and look at my notes. Okay. At 2 seconds, it means between 0 and 2 seconds. If you want to find the displacement from a velocity time graph, which means you want to find the change in position, you do the area between the curve and the time axis in a velocity time graph. So 2 seconds, you have to find this area. 6 seconds, you'll have to find this whole area. We already found this, so you just have to add the area of this house-looking thing. Okay? And at 12 seconds, you just have to add this area and this area. You can see that these two areas are the same, except this one is going to be considered negative and this one is going to be considered positive. So these pretty much are going to cancel out, which means that your displacement at 12 is the same as your displacement at 6. Now the distance. And then we're going to do at 14, which means you just have to add that last piece. And these two already canceled. The acceleration at 2 seconds, well, that's the same as the acceleration anywhere between 1 and 4 seconds. So you just have to find the slope of this segment. Because you find the acceleration from a velocity time graph by doing the slope. And you can do the same thing for 6, 12, and 14. For 6 is the slope of this segment. That's the same as the slope at 12. It's the same as the slope at 14. What is the B-intercept? Well, the B-intercept is here. It means that initially, when the clock started, you started with 0 meters per second. What's the acceleration when t equals 7.5? So 7.5 kind of falls somewhere here. You just have to find the slope of this segment, which you already found. What is the displacement from 1 to 2.5 seconds? So basically, you have to find the area between 1 and 2.5 seconds. You have to find this area. Now just keep in mind, if you find an area that's above the time axis, it's positive. If you find something that's below, then it's negative. Because here, you're traveling in the negative direction, so your displacement is negative. When is the speed increasing? So this is where we have to be super careful. When you're talking about speed, you ignore the plus and the minus. Okay? So it looks like I'm speeding up here, but I'm also speeding up here between 1 and 4, except that I'm increasing my speed here at a lower rate. Here I'm doing it much faster than I'm doing it here. And then I'm slowing down here, but this is what people forget. You're also speeding up here, you're accelerating here. Because you're going from 0 to 100. You have to look at that as 100, not a negative 100. When is the object moving backwards? This is basically just another way of saying when is the object moving in the negative direction. Well, in a velocity time graph, you're moving in the negative direction if you happen to be below the time axis. In a position time, you will be going in the negative direction if your position drops, okay, in time. Or if your steepness is always, or the slope of the tangent is always negative. Okay. Now we need to make an acceleration time graph here. So I'm going to line it up so I can use the same time scale. And I see that one of the accelerations is negative because acceleration is the slope in a velocity time graph. So I have to leave some room down there. So I have one slope here. I have a different slope up to 4, and then from 4 all the way to 14, pretty much one slope. slope here is 40 over 1. So here's your 40. This is acceleration, meters per second, or meters per second square. Time in seconds. So at 40, in the first second, it's going to be 40 meters per second. Between 1 and 4, it's 100 over what? No, not 100. 60 over 3, which is 20. Okay? And then here it's going to be a drop of 200, and it's going to take from 4 to 14, it's going to take 10 seconds to do that. So 200 over 10, that's 20, but it's a negative 20. And this is negative 20. That's that. Pretty simple, right? Okay. Next page. I'm just going to do this page. Maybe I'll skip number 20. So let's just make sure we do this one. And 20 you should be able to figure out on your own. Maybe I'll talk about it just quickly without doing any numbers. Okay. So this one is saying, what's the displacement over the entire trip? But before we do that, let's figure out in what directions we're traveling. This is a velocity time, which means I'm traveling in the positive direction whenever I am above, or whenever the graph is above the time axis. I'm in the negative direction whenever I am below. Okay. If this were a position time graph, you will be traveling in the negative direction each time your position drops. So this is in the negative direction. You'll be going in the positive direction whenever your position increases. That's here. You're not moving here, and then you increase it. You're going in the positive direction. So you just have to be careful how you read these graphs. So the displacement, you just have to find this area, find the area down here between 5 and 25. This has to be looked at as a negative. What time intervals is the object accelerating? Well, you're accelerating when you're speeding up. A positive acceleration does not always mean that you are accelerating. Accelerating means speeding up. So between 0 and 5, you're slowing down. Between 5 and 10, you're speeding up because you're going from 0 to 10. Here you're going from 10 to 5, so you're slowing down. Constant velocity at 5. Or constant speed. Here, you're slowing down. So each time you're going towards the 0, you're slowing down. When you're going away from the 0, you're speeding up. And what's the acceleration? So what did we say we're speeding up? We're speeding up between 5 and 10, so you just have to find that slope. So it's a drop of 10 and a run of 5. So it's negative 10 over 5. What's the meaning of the Y-intercept? It just means like your initial velocity, when the clock started, your initial velocity was 10 meters per second. When is the object moving backwards? That's the same thing as saying when is the object moving in the negative direction. I already addressed that. So it's between 5 and 25 because the curve happens to be below the time axis. When is the object accelerating? We answered that already. Decelerating, meaning like when are you slowing down? Well, you're slowing down here between 0 and 5 seconds because you're going from 10 to 0. Speeding up here because you're going from 0 to 10. Slowing down here because you're going from 10 to 5. Constant velocity here. And you're slowing down here because you're going from 5 to 0. So each time you're approaching the time axis in a velocity time graph, you're slowing down. Each time you're going away from it, you're speeding up. When is the object not moving? We can argue this, but at 5 seconds, think about that. Pause the video and think about what's happening for 5 seconds, and then I'm just going to keep going. So pause it for a few seconds and think about it. At 5 seconds, look, before 5 seconds, the object is moving in the positive direction because you're above the time axis. And here you are moving in the negative direction. The only way you can do that is if you turn around, you change direction. So you have to stop for that split second there and turn. Okay? Now we need to make an acceleration time graph. I see some of the accelerations are negative, some of the slopes are negative, so I have to allow for that. And be careful, not everything is in meters all the time. Not everything is in seconds, so you have to just read the problem carefully. Now the slope here is a drop of 20 over 10 seconds, so that's negative 2. Okay? In here, it's a rise of 5, and you do that over 5 seconds, it looks like, right? So that's a positive 1. Or maybe I should label the times. 5, 10, 15, 20, and 25. Okay, so we say this is negative 2. And then this is a 1. I'm going to try to make it to scale as much as I can. This is a 1. And you're not changing your velocity here, which means no acceleration. So we're taking this line here. And here, the slope is about the same as that. They look pretty parallel to me. Okay? And that's that. So for the next one, I'm just going to talk about it briefly without doing any numbers. If it says, what's the displacement for the entire trip, you just find the areas. Anything that's below the time axis, you have to look at it as a negative area. Anything above, you look at it as a positive. Let me just look here. The next one says, what time interval is the object accelerating? In other words, when are you speeding up? Well, it looks like you're speeding up here between 10 and 20, okay? And you're speeding up here because you're going away from the 0. So between, it looks like about, what, 45 and 50 seconds. And you can find the accelerations by doing the slopes. What's the meaning of the Y-intercept? You can look at the previous problem. When is the object moving in a negative direction? Each time you're below the time axis, you're moving in the negative direction. When is the object accelerating? We talked about that. When is it decelerating? When is it slowing down? It looks like it's slowing down here in the first 10 seconds because you're going from some number, which is negative 20 to 0, okay, which is basically 20 to 0. And you're slowing down here because you're going from 20 to 0, and that's between about 35-ish, 35 to 45 seconds, okay? But down here, you're speeding up, okay? What are we? When is the object not moving? It's at 10 and 45 seconds. There's a change in direction. And we make an acceleration time graph. I'm pretty sure you know how to do that. Okay, and we're done. Thank you very much. See you at the next video. Number 16. And we get to. Yeah. Okay. So this is a velocity time graph. Okay, so they're making some statements, and we have to see which one is correct. The robust displacement is positive because the slope of the graph is positive. Well, the slope in a velocity time graph does not give you displacement. It gives you acceleration. So Arnold is out. Look at Betty. Now the robust displacement will be 0 since it moves in both the positive and negative direction during this time. It does move in both directions, but it spends most of its time in the negative direction than it does in the positive direction. Okay? Because it's staying a lot longer here than it does over there. So she's out too. I think the displacement is negative since the robot has a negative velocity for a longer time. That's what I just said earlier. So you have a negative velocity for 1, 2, 3, about 4.5 units of time. Here you only have a positive velocity for about 3.5 units of time. For these two graphs, these are velocity time graphs. The students are making these statements. I think object 2 will have the greater displacement because it gets to a higher speed faster than object 1. I'm looking at the right one. I think I mixed this up. Okay. I think object 2 will have the greater displacement because it gets to a higher speed faster. Badu says no, object 1 will have the greater displacement because it travels for longer than object 2. I think Andy has the right answer, but for the wrong reason. We can see that object 2 has the larger displacement because the area under the graph is greater. So I think what we need to do here is just find the areas, and which I think we did earlier. So this is 1/2 base times height. That's a 1. I think this is 2. This is trapezoid, so 2 to 5. That's 3 plus 1 is 4. So this is divided by 2 times 2. So that's 4. So the whole thing here is a positive 5. And here I think we did it earlier. It was a positive 6. Okay? So I think Connor is correct here. Let's look at number 18. Okay. Now this one is talking about distance traveled. Okay, not displacement. So we have to find the displacement and change them into distances. Okay. So what it's given us here is given us from 4 to 6 seconds. It's given us that graph. It says that it covers 6 meters. So from 4 to 6, so what is that? 2 times 3, that's 6, right? Okay, that's the area there. Okay, so all we have to do is find the area between 0 and 2, 2 to 4, and all that stuff, right? So from here, for 0 to 2, it's 1/2 the base times the height. Okay, it's negative, so this is going to be a -3, but in terms of distance, that's a positive 3. So if this is 1, 2, 3, 4, if that's taken 6 bars, this is going to take 3 bars. And you shade that area. Then you do the same thing for this part, which looks like these 2 triangles are, what do you call them, identical. So we're just going to cover the same amount, same area. This one looks about the same as this one, so it's the same thing here. Okay. This one looks different from E to 10. So let's figure out what that area is. So it's 1/2 the base, which is 2, times the height, which is 2. So it's a 2. So this one is here. Okay. And the next one is this area here, which is 2 times 2, which is a 4. So that's 1, 2, 3, 4 here. And then from 12 to 14, you have to do each area and you have to add them. Okay? In terms of displacement, it looks like it's 0, but in terms of distance, it's something else. So it's 1/2 the base, which is, I'm looking at this little triangle here, basically, which is 1 times the height, which is 2. So that's a 1. And then you have another 1 on top of it. So that's should be 2 bars in there. Okay. Number 19. Alright, for number 19, this is talking about the instantaneous velocity, right? So rank these situations on the basis of velocity at the point indicated. So the velocity here, since this is a position time, is just the slope of that line. Okay, and it doesn't say the magnitude of velocity, so the negatives do matter here. So it's 1, 2, 3, so that's 3 over 6, okay? This here is going to be, I'm just going to find the slope of this whole thing. And the further apart the points are, the better value you're going to get for the slope. So it's going to be definitely negative, and it's going to be a drop of 2. Yeah. And a run of, it looks like it's 1.5. Okay? So this looks like it's about -4/3. This guy here looks like it's, you rise by 2, and it's +2, and you run 4. So this is just half. This is also half, positive. This guy here is a rise of 1, and a run of 1, 2, 3, 4, 5, 6, positive. This one here is a drop of 1, so that's a negative, and a run of 6. This guy here, I'm going to go between these two extreme points here, so it's 1, 2. That's a drop of 4, and a run of 3. So let's rank these velocities. So I'm going to get rid of all this extra junk here. Okay. So which one is the highest? It looks like it's A and B. Yeah, this is A and B. Okay. And then comes, so this is done. Then comes E. That's done. Then what else? And then comes F. That's done. And B and C are last. Okay. All right, let's look at number 20. So here we're looking for the average velocity. Okay. To find the average velocity, we just add up the velocities and divide by 2, I guess, right? Because it's a constant acceleration. So this is just going to be you're going from 0 to 2. So it's going to be 2 over. So this is a 1 in here. This is going to be 0. This one is going to be -2 plus 0. So this is going to be -1. This guy here is going to be 1, positive. This was positive. This one is going to be this value, which is -1 plus, so that's going to be 0. And this one here is just going to be, looks like it's also 0. Okay, so to rank this, it's going to be A and E together. Then comes D, C, and F all together. And then the last one should be B. Okay. So your position is positive, so you are to the right. So it's giving you an example here. the velocity is positive, okay? So you're going away from the origin, it looks like, right? Yeah, that's what it means by towards or away. And speeding up or slowing down, you speeding up because your acceleration is positive and you're going to the right. Okay, so we're going to use this idea here. Your acceleration will be positive if you're speeding up in the positive direction. Okay, it can also be positive if you're slowing down in the negative direction, and this will be negative if you're speeding up in the negative direction, or if you're slowing down in the positive direction. So that's how we're going to do this. All right. So here your position is positive, which means you are on the right side. Okay, so I'm going to fill in the positions first. So right, 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 left, 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 left. Okay. The direction, if your velocity is positive, you're going away from. So away. If your velocity is negative, it means you're going left, which means you're going towards the zero here. So here you're starting from the right, and you're going towards the zero. Okay. Here you're starting from the right, and you're going towards the zero also. Right. Here your velocity is positive. Okay. And you are on the left side. Okay. So your velocity is positive, and you are on the left side. So which means you're going towards the zero. In here, you're starting left, you're starting on this side, and the velocity is positive, which means you're also going towards it. If you are on the negative side, and your velocity is negative, which means you're going left, so you're going away from the zero, and the same thing for the last one. Okay. All right, let's look at the acceleration. In the first case, the velocity is positive, so you're going this way, okay? And you're going in the positive direction, okay? So your acceleration is positive, you're going to the right, so you must be speeding up. Okay. No, I was looking at the wrong one. So it's already saying speeding up. Okay, your acceleration is negative here, so you're here basically. Your velocity is positive, your position is positive, so you must be slowing down. Okay, I'll fill in the other ones. All right, so in this one here, your acceleration is negative, and you're traveling away from zero, right? Okay. So that's why you're slowing down. Okay? All right. So let me take a look at another one. Okay. Or let's look at this one here. So here your acceleration is positive, okay? Your velocity is positive, and your position is negative. So let's try that. So you are here, okay? Yeah, you started here, your velocity is positive, so which means you're going in that direction, and your acceleration is also positive, okay? So when the acceleration and the velocity are in the same direction, it means you are speeding up. When they're in opposite directions, it means you are slowing down, okay? And that's it. Basically, you can just look at the product of these two signs here. So positive times a negative is a negative, so which means it's slowing down. This should be slowing down. It should end up giving you a positive, which means you're speeding up, positive and negative means you're slowing down, and speeding up at the end. So you can just multiply the product of the sign. You can multiply the signs of velocity and acceleration to figure out whether you're speeding up or slowing down. All right, let's look at 22. So we have to rank them based on acceleration. And it does not say magnitude of acceleration, so we're going to keep the negatives in there. So the acceleration here is basically just the slope of these segments here. So it's 2 over 4, so half, positive half. This one, you go from, it's going to be definitely a negative slope. So you go from 2 to negative 2, that's a drop of 4 in 4 seconds. So that's a negative 1. This one here is a rise of 2 in 4 seconds, so it's a positive half. This one is a drop of 2, which is negative 2 in 4 seconds, so negative half. This one here is a drop, it looks like it's 2, so negative 2 in 4 seconds, negative half. And this one here is a rise of positive 2 in 4 seconds, so that's a positive half. So which one has the highest acceleration? It looks like it's A, B, and C are tied for the first place. A, B, C, we'll put a circle around them. Then comes E and F for 4th and 5th place. And it looks like D is last with a negative 1. Okay.